metals from their ores, right? The extraction of metals from their ores. There are three major steps. One is the concentration of the ore. The other is the extraction of the metal from that ore, from that respective ore. And the third is the refining of the metal, right? Third is the refining of the metal. So we have done the first two steps. The first one is not that much discussed in our syllabus. The second one is the extraction of metal from their ore, and that is basically one of the deciding factors as to what type of method will be used to extract the metal from the ore is the type of the metal based on its reactivity, right? So it is according to the reactivity of the metal that we have different methods according to which we can actually extract the metal from their ore. Yes, Rebunisa?
Yes, ma'am.
So the most reactive metals like sodium, potassium, calcium, magnesium, aluminium, they are actually extracted by which method? They are extracted by their electrolytic refinement, right? Sorry, electrolytic reduction. Okay, the electrolytic reduction of their ores. Therefore, once they are reduced from their ores to the pure metal, they are reduced from the ores to the pure
Metal.
metal. Okay. Second one was the, and very important point here, since we are reducing them by the electrolytic reduction, they are already pure. So there is no need of refining the metals which are the most reactive metals. Okay, that's one very important point. Okay. Now, second, coming on to the moderately reactive metals, zinc, iron, copper, all of these things basically, how are they reduced? How are they actually extracted? Through the reduction. Now, what is actually reduced? The oxide is reduced. What is used as the reducing agent? The carbon is used as the reducing agent. Okay. But to change to their oxides from their sulfides or the carbonates, what are the different methods used? Either it is calcination or roasting. Either it is calcination or roasting. If
Roasting.
there are sulfide ores, they are changed to the oxides via the roasting method. That is heating in presence of oxygen. If they are carbonate ores, they are changed to the oxides via calcination. That is heating in the absence of oxygen. Okay. So I hope that point is clear.
Yes, ma'am.
The last, that is the least reactive metals. Okay, examples, the silver, the gold, all of these, most of them are actually found in their native states without any bonding. But if they are found in any of the ore like sulfide or carbonate, they'll first be reduced to the oxide, and once they have been changed to the oxide, they do not need any reducing agent as such. They can just be reduced by simple heating. Therefore, just by reducing, we can have the metal. Okay. And along with the metal, what we'll get? We'll get the oxygen gas. Okay. Along with the metal, what we'll get? We'll get the oxygen gas. Example, let's take the example of cinnabar. What is cinnabar? HGS, the ore of mercury. The ore of mercury.
Mercury.
Okay. So it is like this. HEGS. Now we know that mercury is a very less reactive metal. Okay, the third category of metals. So what we'll do first, we'll change it to the oxide. How can we change it to the oxide? By roasting. Why? Because it's a sulfide ore. Why? Because it's a sulfide ore, huh? So we'll change it to the oxide by roasting, right? By roasting. Once we have changed it to the oxide ore, we'll simply heat it. We don't really need any reducing agent, and it will form the mercury plus oxygen gas. And here it will form the sulfur dioxide. That's it. Okay. This is the reaction that we'll be having. Any problem in this?
No.
No. And the third step is the refinement of the metals. Before starting this, let's quickly go through the NCERT. Okay. See, from here we had to start. Yes. You have understood what are minerals? Minerals contain a very high percentage of a particular metal, and the metal can be profitably extracted. These are called as ores. Okay. The second one, extraction of metals. Some metals are found in the earth's crust in the free state. These are very less reactive metals, right? Gold is found in the free state. Some are found in the form of their compounds. Compounds, they are nothing but the ores, right? In the form of compounds, they are bonded to something. That is why they are forming a compound. The metals at the bottom of the activity series are the least reactive. They are often found in a free state. Yes, bache? Example, gold, silver, platinum, and copper are found in the free state. Zebednasa, am I audible?
Yes, ma'am.
Okay, okay. So keep on responding because your camera is also off, right? So I'm not
Yeah.
getting to know it. See, copper and silver, although they are less reactive, they are also found in the combined states. Okay, so there are two states, either free state that is without any bonding, or the combined state that is in the form of a compound, and that is nothing but ore. Okay, see, they're sulfide or the oxide ores. The metals at the top of the reactivity series, please, this is very important. Okay, sodium, potassium, calcium, magnesium, aluminum, they are very reactive, the most reactive. Okay, they are actually reduced by electrolysis reduction. Electrolysis or electrolytic reduction, okay, are so reactive that they are never found in the nature as free elements. The metals in the middle of the activity series, zinc, iron, lead, etc., are moderately reactive as oxides, sulfides, or carbonates. You will find that the ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on Earth. This is a very important point. I think in the last class also I pointed this out. Oxygen is a very reactive element and is very abundant on Earth. Therefore, many of the metals will be present in what type of ore? In the oxide form. What type of form?
Oxide form.
Oxide form. Good. See, several steps are involved in the extraction of pure metal from ores. We have the summary here. See, bache. First, we have the ore. We will concentrate the ore. Okay. First, we have the ore. We will concentrate the ore. Once the ore has been extracted, we will extract. Sorry. Once the ore have been concentrated, we will extract the metal from the respective ores. Right. Now, for
Yes.
different metals, we will use different methods, metals of high reactivity, metals of medium reactivity, metals of low reactivity. So we will just go through the electrolysis of molten ore. Very important, molten ore. Why are we using molten ore? Hanji. Why are we using molten ore? Because it is in the molten ore, I mean, it is in the molten state that the ore will actually behave like the ions which will conduct electricity, right? They will be mobile. If they are not, if they are in the solid form, the electric current will not be passed. If there's no
So only
electric
in the
current,
molten form.
so they will be in the molten form, okay? Simple
Okay.
reason, they'll behave as the mobile charge carriers, right? Carriers of current. Mobile, that is moving. If they are in the solid form, they cannot really do that. And the basis of this is electrolysis. Are you getting it?
Yes.
And we get the pure
But
metal.
how are we going to convert it into the molten form? By
Just heat it.
electrolysis.
No, 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 no. We are not going to change it into the molten form by electrolysis. Okay, let's suppose we have any ore. Okay, we can heat it somewhat. The temperature could be raised.
Yes.
It has been changed to the molten form. Now it is in that molten form that we'll perform the electrolysis there. Okay,
Okay.
is it clear now?
Yes.
Fine. Now, metals of medium reactivity, if we have carbonate ore or sulfide ore, we'll change it to the oxide in both the forms. Calcination, roasting, reduction of metal. How are we going to reduce the metal? There are two methods, huh? There are two methods. Can you tell me? First is carbon.
Car-
The other
car-
is a more reactive metal. Yes, we saw that in the last class.
Yes.
Yes or no? A more reactive metal, but you always remember a more reactive metal will actually reduce, will behave as a reducing agent. Okay. Why? Because itself it will get oxidized. And then the purification of metal, sulfide ores, roasting, metal refining, that's it. Clear?
Yes.
See, this is important. What is gangue? I think in the last class also I discussed it. Impurities such as soil, sand, etc. are called gangue. Okay. When we are
Yes.
concentrating the ore, not when we are refining the metal, please be clear. When we are concentrating the ore, then what we get is the impurities that we call as the gangue. Okay. That's it. See, extracting metals low in the reactivity series. Cinnabar, please know these names. Cinnabar is HGS, okay, sulfide ore of mercury. Sulfide ore of mercury, okay. When it is heated in the air, see, sulfide ore, so it means it has to be changed to the oxide first, yes or no?
Yes.
Yes. How can we change it to the oxide
So
from
when we are
sulfide?
heating the HGS
Uh-huh.
oxide, it's turning into the
No,
molten form.
no, bache. That we are saying for the most reactive metals, okay?
Okay, only for the
HGS,
most reactive.
here we are talking about the metals which are low in reactivity series, okay?
Okay. Okay.
Fine. So here we are not even using the electrolytic reduction method. Okay. Okay, Zip?
Yes, ma'am.
Yeah. So 2HGS, that is the ore of mercury, sulfide ore. So at any cost, we will first have to change it to the oxide ore. How can we change it to the oxide ore? By heating in the presence of oxygen. So therefore, plus 3O2 heating will give us oxide of mercury plus sulfur dioxide. Then we can reduce this simply by heating. Why? We don't need any carbon here because this is a very less reactive metal. So we don't need the reducing agent, right? So mercury plus oxygen. Is it clear?
Yes, ma'am.
You should know these reactions very clearly, including the states here: solid, gaseous, okay, liquid, gaseous. All of these are very important. Similarly, copper, which is found in the copper sulfide in nature, can be obtained. See, how can we obtain it? Again, copper sulfide. So first change to the oxide form by heating in the presence of oxygen. We get copper oxide plus sulfur dioxide, right? Then we have copper dioxide heated again here. Okay, this part plus this part. They are basically saying that what is happening here? We are having the oxide form here. Okay, and then we are reducing it by heating. What are we getting? What are we getting here?
Com-
Copper,
Copper.
the metal from the ore. Yes or no?
Yes.
Yes. Yes. Okay, that's it. Fine. Now, extracting the metals in the middle of the activity series. Uh, the same thing, except that we are reducing the oxide using some reducing agent. Beside using carbon to reduce metal oxides to metal, sometimes displacement reactions can also be used. Yes. The highly reactive metals such as sodium, calcium, aluminum, etc. are used as reducing agents because they can displace metals of lower reactivity from their compound. This is very important. Okay. When manganese dioxide is heated with aluminium powder, the following reaction takes place. See, manganese oxide, aluminium being more reactive than manganese, will actually displace manganese from here and will form aluminium oxide, and here manganese will be reduced to pure metal. Yes.
Yes, ma'am.
Now see, next point. Acha, can you tell me what is being reduced and what is being oxidized here in this reaction?
In this reaction, aluminum is being oxidized
Good.
and
Aluminium is oxidized from aluminium to aluminium oxide. Very good.
manganese is being reduced.
Uh-huh. So manganese oxide is reduced to manganese. That is the metal form. Okay. That is how you will say it. Good. These displacement reactions are highly exothermic. That means a large amount of heat is reduced. I mean, is evolved. Okay. Released. The amount of heat evolved is so large that the metals are produced in the molten state. See, here
Oh,
also we see the metals in the molten state. Here also we see the metal in the molten state. This is a very important point here. Okay. The reaction of this, see, bache, iron oxide plus aluminium. We'll have the same reaction, aluminium oxide plus iron. Now, iron is formed in the liquid state. Why liquid? Because this heat will change this iron, pure iron, from the solid to the liquid state. Okay. And it is used to join railway tracks or cracked machine parts. We use iron for all of this, right? And how can we actually use it as a joining sticking agent when it is in the molten form, right? So this reaction has this application. What's the application of this? Iron oxide plus aluminium. That we get the iron in the molten form due to the large amount of heat released, and that molten iron could be used in joining the tracks or cracked machine parts. Is it understood? This reaction is called as a thermic reaction. Hello.
yes, ma'am.
Fine. That's a very important point. This iron being heavy will settle down and aluminium oxide will actually somewhat float over this iron, okay? Because you will have this question in some of the, I think the exemplar, the NCRT exemplar, wherein you have this question, okay? So be mindful of this, that aluminium oxide might float over iron because of the density difference. Clear?
Yes.
Now, so we have extracted the metals which were low in the reactivity series, in the middle of the reactivity series. Now we are going to talk about the metals which are at the top of the reactivity series. Okay. See, the metals high up in the reactivity series are very reactive. They cannot be obtained by heating with carbon. Why can't they be obtained by heating with carbon? Actually, we cannot use the more reactive metals for the most reactive metals, right? What metal can we use for them if they are already themselves very reactive metal, correct? So we cannot use the displacement reaction for them. Yes, Zeb?
Yes,
And we cannot also use carbon. Let's see why can't we use carbon? Because Carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminium to the respective metals because these metals have more affinity for oxygen than carbon. See here. Let's suppose sodium is present in the oxide form, okay? If you want to reduce it, we can use carbon, right? So carbon will bond with oxygen, huh? And we will
Mm.
get pure sodium, something like this. Yes or no?
Yes.
But this is not possible. Why? Because here the more reactive metal, the most reactive metals, that is sodium, potassium, calcium, magnesium, aluminium, they have such high affinity for oxygen that the affinity of oxygen towards carbon is less than that. So it is very obvious that oxygen will stay with sodium, right?
Yes.
So if oxygen stays with sodium, we cannot get pure sodium, right? Therefore, we do not use carbon as the reducing agent. What do we use actually for the reduction? We use electrolytic reduction. See, electrolytic reduction. Therefore, these metals are obtained by electrolytic reduction. Sodium, magnesium, calcium are obtained by the electrolysis of their molten chlorides. The same thing. The metals are deposited at the cathode, whereas the chlorine is liberated at the anode. Why are we having chlorine here? Because we are reducing what? The molten chlorides, right? At cathode, we will have sodium plus electron will give us the pure metal sodium without any impurity. And anode 2Cl minus will form the chlorine and it will release 2 electrons. Hello.
Yes, ma'am.
Is it clear, bache?
Can you explain this equation again?
Yes, I can. See. Here. What are we having? We are having NaCl, huh? This is the chloride ore for sodium. Let's take the example for sodium, correct?
Yes.
This is the ore, huh? This is the ore. Now, what do we want to do is that we want to extract the metal, right?
Mm.
Extract the metal from the ore. What do? We want to reduce it, right? We want to reduce it. We want to reduce it, right? Since these are already themselves the most reactive metals, we cannot use more reactive metal for them. Therefore, we cannot use the displacement reaction, right? Yes or no?
Yes.
The displacement option is gone. The second one, carbon as reducing agent. That also we cannot use. Why can't we use? Because oxygen has more affinity
Yes,
towards them
ma'am.
than carbon. Yes. Yes, Zeb.
Yes, ma'am.
Fine. Now, what option are we left with? We use electrolytic reduction. We use electrolytic reduction. Reduction in the presence of electric current. That's it. So let's quickly get the setup here. Okay. This is the molten NaCl. NaCl, huh? These are the two electrodes. These are the two electrodes. This is a negatively charged one. Negative electrode, which is called as cathode. Huh? This is a positive electrode, which is called as anode. This is nothing but the setup for electrolysis, right?
Yes.
Once the current pass through this, okay, don't you think it will actually change to this one, Na plus Cl minus, because it is in the molten form? And once the current starts passing to this, don't you think this Na plus will be attracted to the negative one, which is cathode? Cl minus will be attracted to the positive one, which is anode. Huh?
Yes.
So at cathode, what will happen? Cathode is negatively charged, right? So sodium plus will take one electron from what? From the cathode. And what will it form? Sodium, no? It was positively charged. It gains one electron back. It forms a sodium element. Yes or no? Metal.
Mm.
Not clear.
Yes, ma'am.
Clear. Now see, chloride, which was minus, it will have to lose one electron. So see here what happens. Don't you think it is happening like this? Why? Because it is losing one electron. Look here. Two chloride ions lost one electron each. Now together they have formed Cl2. And what is happening? Two electrons are lost. Yes or no?
Yes, ma'am.
Is it clear now? So these are the equations. This is for cathode and this is for anode. Any problem with?
No, ma'am.
In the similar manner, aluminium is also obtained by the reduction of the aluminium oxide. Again, aluminium on cathode, oxygen on the anode, right? We'll have O2 on the anode, we'll have aluminium, pure aluminium on the cathode. Any problem?
No, ma'am.
No. Let's quickly see one thing here, if they have written it or not. Now come to the refining of metals. Once we have got the metal, how can we refine it? Actually, the most reactive metals will not be refined. We are already reducing them through electrolysis. Therefore, they do not need the refinement. They are already very pure. Fine. See, the metals produced by various reduction processes described above are not very pure. Impurities which must be removed to obtain pure metals. Huh? The most widely used method for refining impure metals is the electrolytic refining. Electrolytic refining. The method that we are using for the most reactive metals for the extraction of metals from their ores was electrolytic reduction. Here, what are we doing? Electrolytic
Refining.
refining. In both the methods, we are using electrolysis, but the purpose is different, huh? The purpose is different, okay? Now, see electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold are refined electrolytically. In this process, I'll tell you all of this here through the diagram, okay? Let's see. We are starting this part, okay? The refinement of the metal. Let's suppose I have to purify copper. I have to get pure copper, okay? From whatever metal I have gotten, I want to get the pure metal, okay? That is copper. So what will I do? I will have the setup for electrolysis, okay? I will take any aqueous salt solution of the copper. So I can take copper sulfate solution here, okay? Copper sulfate solution, clear? In the presence of acid. In the presence of acid, why acid? Because why here? Because it will obviously dissociate. Okay. Now see what happens. What we do, I take the metal that I have gotten here, okay, and that will be the impure copper. What will that be?
Impure copper.
Here I will use a very thin part as an electrode. What? This is already pure copper. Let's suppose I have pure copper, okay. I will use here, okay. I will pass the current here like this, okay. It will be the anode and it will be the cathode, okay. It will be the cathode and it will be the
Anode.
anode. Clear? Is it clear till here?
Yes.
As soon as the current would be passed, don't you think from this here, what is it? Copper plus impurities. So copper will start moving towards the cathode. Copper will start moving towards the cathode, and impurities from here will settle down here in the form of anode mud. What will it call be?
Anode mud.
Anode mud. Just below this one, anode, huh? These are nothing but impurities. What was there on this? It was copper plus impurities. So copper will move to this one towards the pure copper, right? Yes or no?
Yes.
Because it is cathode. Copper being a metal will be attracted towards the cathode. So, and what we'll see gradually, the impure part will keep on getting thin and the pure part will keep on getting thick. Why? Because the copper from this impure will keep on getting deposited at the cathode, yes or no?
Yes.
So, impure part gets thin and pure metal gets thick. Is it understood? Yes or no?
Yes, ma'am.
So basically what are we using as the electrolyte? Some metal salt, okay? Metal salt solution we are using as the electrolyte. Whatever metal we are refining, we'll use the metal salt solution of that metal, correct?
Yes.
That's it. Any problem here?
No, ma'am.
No. See here. Let's quickly go through this. The anode, just 1 second, bache. See, The impure metal is made the anode, and a thin strip of pure metal is made the cathode. A solution of the metal salt is used as an electrolyte. Very important. The apparatus is set up like this. Fine. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. Yes or no? An equivalent
Yes.
amount of pure metal from the electrolyte is deposited on the cathode. On the cathode, the
Cathode.
soluble impurity is going to the solution whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. So basically, the soluble impurity will be dissolved in the solution, and the insoluble will be deposited as the anode mud. Clear?
Yes.
See what is happened as soon as the current would be passed, the the impure this thing electrode, right? See what is happening here. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. Okay. On the anode, what do we have? The impure metal or the pure metal?
On the anode, we have the impure copper.
Anode, we have the impure
Copper.
copper, right? So as soon as the current is passed, so the copper from the impure copper will be dissolved in what? The electrolyte. Okay. And therefore, we'll have the electrolyte giving the copper back again to the pure metal. Are you getting this cycle?
Yes.
Like this. Okay. And why are we using a metal salt solution of the same metal? Because of this reason. It will be providing the metal, right? Are you getting this?
Yes, ma'am.
Fine. On passing the electric current, pure copper is deposited on the cathode. On the cathode. Cathode, we have what? The pure copper or
The
the
pure
metal
copper.
strip. Yes. Any problem here?
No, ma'am.
That's it. So the occurrence of the metals is clear. I hope there should be no problem. Now define the following terms. The mineral ore gangue I have already discussed. Name two metals which are found in the nature and free state. Again, very simple. Platinum, gold, they are always found in the free state. What chemical process is used for obtaining a metal from its oxide? What chemical method process is used for obtaining a metal from its oxide? Hanji. Reduction. Are we not reducing it again and again? Either by heating or by using a more reactive metal or by using carbon as the reducing agent, right? Or by electrolytic reduction. That's reduction. Clear?
Yes, ma'am.
Should we start with this one? Corrosion. See here, 2 to 3 this we have already discussed in the first chapter, so we'll quickly go through this. Silver articles become black and black after some time when exposed to air. This is because they have a layer of silver sulfide. See here. Let's suppose this is silver, huh? This is silver. It reacts with this which is present in the air. What will happen? It will form silver sulfide, and this gives black color. This gives.
Black color.
Or if we have, silver, it reacts with oxygen. So what will it form? Silver oxide. Again, it is called as tarnishing of silver. Clear? So when silver is corroded, what is it called as? Tarnishing of silver. What is it called as?
Tarnishing of silver.
And what is actually being formed? Mostly it is this silver sulfide which gives the black color. And black color, when silver metal changes to black color, it is called as tarnishing of silver, which is nothing but corrosion of silver. Okay?
Yes.
When copper, see, important, copper reacts with moist carbon dioxide in the air and slowly loses its shiny brown surface. Pure copper, which is a metal, will have the shiny brown surface. Once it is corroded, what will happen? See, we have copper, we have carbon dioxide, and we have water. Huh? Obviously, we have oxygen in the air, moist carbon dioxide, very important. So what will it form? It will form this copper hydroxide dot copper carbonate. Okay, dot copper carbonate. And what is this called as? A basic carbonate. What? Basic copper carbonate. What color is this? Green color. What color is this? Green color.
Green color.
So this is also nothing but the corrosion of copper. What is this? The corrosion of copper.
Copper.
Basic copper carbonate. What's the formula? Please write the formula very carefully. CuOH whole twice dot copper carbonate. Okay. Basic copper carbonate. Why basic? Because this means basic. Huh? Copper hydroxide is basic. They've written. Done.
1 second.
Acha, acha. I hope I'm not going too fast. If yes, please let me know.
No, ma'am.
Okay.
Done, ma'am.
That. See, iron also gets corroded. What is it called as rusting, huh? And what is rust chemically? Fe2O3 dot XH2O. This is nothing but rust chemically, huh? This is rust. Chemical formula, ferric oxide, hydrated ferric oxide.
Now let me just copy it.
Yeah, yeah. Is it clear? Should I write it properly?
No, no, it's clear.
Okay.
Yes, ma'am, done.
And what is the color here? Brown color, right? So we have discussed three metals for their corrosion. I'm repeating it. Please listen. Silver. What is it called as tarnishing of silver? What color is it? Black color. What is the
Black.
compound? Silver sulfide, huh? Silver
Yes.
sulfide or silver oxide, whatever we have.
Silver oxide.
The next one is for copper. The compound formed is called as the basic copper carbonate. What color is it? Green color.
Green.
What is the formula? Copper hydroxide dot copper carbonate. Okay, CuOH whole twice dot CuCO3. Correct?
Yes, ma'am.
The third metal is the iron, which is very clear, which is obviously the moist oxygen or the moist air. And iron plus water plus oxygen will give us the ferric hydrated oxide, I mean ferric oxide, which is hydrated. Fe2O3 dot XH2O. What does X indicate here? The amount of water vapor present in the air. We have more water, we have more humidity, the amount of X will be more. If we have less humidity, the amount of X will be less. Okay.
Yes.
And what color is it? Brownish color. You know the color of rust, right? Brown
Yes.
flaky substance, that is rust. Any problem here? This is a theoretical question, could be asked very, like many questions could be framed from this. Just these 3 points. Clear, bache?
Yes, ma'am.
Fine. Now, how can you prevent this? See, very easy. Basically, we have the prevention for the rusting of iron. So what can we do, or the rusting of corrosion of anything? What can we do? Basically, we need to prevent the contact of the metal in the moisture. That is what we need to do, right? The prevention of
Yes.
the we need to prevent that contact. So there are many methods in which we can prevent. See, bache here. I'll not go through this. You can go through this very clearly, but I'll discuss exactly what is written here. See, we have the nails in this figure I'm talking about. Okay, we have the nails, we have water, we have air, but there is nothing which can prevent the contact between air, water, and the nails. So obviously it will get rusted. You can see it; they get rusted, right? This
Yes.
part would be understood. Now let's see here what is happening. We have air, we have water, we have nails. Okay, but yet we do not get this rusted. Why? The nails here are clean. Why are they clean? Because we have a layer of oil here, and that layer of oil prevents the contact between air and the metal. The metal is here, the air is here, right? There is no contact between them. If there is no contact between them, obviously there is no oxygen. Therefore, no corrosion will take place. Is it understood?
Yes, ma'am.
Prevents air dissolving in the water. See, Acha, the question could be asked, but there is water around the metal. So why is it not getting rusted? Because for the rusting of iron, what do we need? Oxygen and water. Here, the air is not reaching the metal. It is not getting dissolved in the water. Therefore, no rusting will take place. Fine, bache.
Yes, ma'am.
What is the third thing that we can do here? What we have, see, bache, we have the iron metal. We have air, which is dry. Why is it dry? See, air we have, that means oxygen we have, right? What do we need the next thing? That is water. Why are we not having water here? See, we have anhydrous calcium chloride. I'll write the formula CaCl2. Anhydrous calcium chloride. This absorbs the water. What does it do? It absorbs the water. Okay, so when it is absorbing the water, there's nothing like no water is left in the this thing test tube. So when there's no water left in the test tube, don't you think the air will be dry? And if air is dry, obviously no rusting will take place because water is a component for the process of rusting to take place. Yes or no?
Yes, ma'am.
That's it. Is it understood? Any problem here in this diagram?
No.
No. This activity is telling the same thing. I've discussed the points here. Okay,
Okay.
now what are the methods to prevent corrosion? We just want the contact to be broken. What are the different manners in which we can break this? See, prevented by painting, oiling, greasing,
Greasing.
galvanizing, chrome plating, anodizing, or making alloys. Painting, again, it is breaking the contact. Oiling, greasing, they are all breaking the contacts. Let's understand what is galvanized. But you see, we have iron. We have iron. If we have oxygen plus water, obviously oxygen will attack iron and it will get oxidized. What will it do? It will get oxidized. Rusting is nothing but the oxidation of iron. Okay, rusting is nothing but the oxidation of iron. Corrosion is nothing but the oxidation of the metal. Corrosion is nothing but the oxidation of
Oxidation of metal.
metal. So see now here what happens? This iron gets rusted. That means it gets oxidized, it gets corroded. It gets oxidized, it gets corroded. How can you prevent this? See, If we have a metal here which is more reactive, so don't you think oxygen will first combine with that metal which is more reactive? Yes or no?
Yes.
So that is what we are doing. Instead of iron, we are having a layer on it that is for zinc. Now, zinc is a more reactive metal than iron. Okay, let's
Iron.
suppose we have the iron object and we have the zinc layering here. Okay, so what will happen? Oxygen and water, instead of combining with iron, what they'll do? They'll combine with
Combined with zinc.
zinc. Huh? And here, instead of iron getting oxidized, zinc will get oxidized. Zinc will get oxidized, huh? And iron gets reduced.
Reduced.
And when it's reduced, definitely it is forming the pure metal. We saw that in the extraction of metals also, reduction will give us pure metal. Yes or no?
Yes, ma'am.
So here the more reactive metal, which is zinc, gets oxidized, and the less reactive metal, which is iron, is safe, is a pure metal. That's the only thing which is galvanization. So galvanization is nothing but the plating of zinc on the iron objects through the electrolysis. The plating of zinc through the, the plating of zinc on the iron objects through the electroplating method. Is it fine? Is it fine?
Yes, ma'am.
Okay. Acha, chrome plating, same thing. Instead of this thing, we are actually using some other metals here. Okay. Nickel, chromium, all of that. So we are basically using metals which could prevent the oxidation of iron. Fine. The next one, anodizing. We will discuss this in detail, or making alloys. Again, why can we use alloys? We'll discuss this in detail. See, galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of
Zinc.
zinc. The galvanized article is protected against rusting even if the zinc coating is broken. Can you reason this out? See, basically what has happened, let's suppose this. Okay, this is iron. We had the zinc layer here. Now it will react with oxygen. Obviously, zinc is finished. Okay, every zinc has reacted here. Every particle of zinc has reacted here. Don't you think here the layer of zinc oxide has formed? Now the oxygen cannot really attack iron here. So therefore it is still safe. Fine.
Yes.
I think I'm going too fast for you.
No.
Pakka?
Yes.
Fine. See, alloying is a very good method of improving the properties of a metal. What is alloy?
Alloy is the mixture of
Good.
metal
The
and non.
homogeneous, excellent. The homogeneous mixture of either two metals or metal or non-metal. Yeah. Whatever we have, more than two metals, whatever. Yeah, good. Why do we do this? See, because we can get the desired properties by this method. Iron is the most widely used metal, but it is never used in its pure state. It is used
No.
in the alloy form, huh? Because pure iron is very soft and it stretches very easily when hot. But if it is mixed with a small amount of carbon, that is just 0.05%, it becomes hard and strong. We have seen the iron we use that is very hard and strong, right? That is because
Yes.
of the presence of 0.05% of carbon in that iron. When iron is mixed with nickel and chromium, we get a stainless steel. Very important. It's an alloy which is hard and does not rust. Again, nickel and chromium, they will not actually react with the oxygen and then it will not rust. Thus, if iron is mixed with some other substance, its properties change. In fact, the properties of any metal can be changed if it is mixed with some other substance. That is nothing but the properties of alloys. The substance added may be a metal or a non-metal. Alloy is a homogeneous mixture of two or more,
Metals.
or a metal and a non-metal. It is
Non-metal.
prepared first by melting the primary metal and then dissolving the other element in its definite properties. It is then cooked to room temperature. See what we do. What is the method of preparation of alloy? Let's suppose I have to make the alloy of iron. My iron is the primary metal, right? So what we'll
Yes.
do? We will melt iron. Okay, we will melt iron. Then we have melted iron. We can add the required proportion of carbon to this. We can add the required proportion of carbon to this. Once we have got the mixture, we can actually solidify it or cool it to the room temperature. So then it becomes the solid. Yes,
Yes, ma'am.
that's it. Now see anodizing. Quickly, let's go to anodizing. What is anodizing? First, quickly see the properties of the alloy. Then we'll go with the anodizing. Acha, very important. If we are making any alloy with the mercury, what is it called as? Amalgam. Amalgam of anything. Why? Because amalgam refers to mercury here. See, if one of the metals is mercury, then the alloy is known as amalgam. Clear?
Yes, ma'am.
The electrical conductivity and the melting point of an alloy is less than that of pure metal. This is a property of the alloy. The conductivity will be reduced, the melting point will be decreased for the alloy. Okay, for the alloy. then it's pure metal. Brass and alloy of copper and zinc, and bronze and alloy of copper and tin are not good conductors of electricity, whereas copper is used for making electrical circuits. Copper is a very good conductor of electricity, but its alloys are not. Why? Because they are alloys, okay? Solder and alloy of lead and tin has a low melting point and is used for welding electrical wires together. Is it okay, bache?
Yes.
So now can you tell me the components of the stainless steel? Stainless steel is an alloy.
Yes.
Can you tell me the components here?
Stainless steel.
See,
Iron, silver.
no. Iron, carbon plus nickel plus this
Okay.
thing, chromium, huh? That's it. This gives us iron and this gives us stainless steel. Iron plus carbon basically gives us a steel, no? And then we are using nickel plus chromium, that is giving us stainless steel. Clear?
Will they ask this in the exam? Like
It
this
could
type
be
of
asked
question?
because it is written in the NCRT. Did we not see it? See, we saw it here. See, bache. When iron is mixed with nickel and chromium, we get stainless steel. It's written in the NCRT. We can ask it. Huh? What's the component for this? What is the component for this solder? Can you just give me 1 second? Just one
Yes, ma'am.
second, huh? Thank you. Yes, Epanya, sir. Okay. See, okay. Solder is an alloy of lead and tin. Solder is an alloy of lead and tin. Brass is an alloy of copper and zinc. Bronze is an alloy of copper and tin. And the first discovered alloy was bronze. What's the first discovered alloy?
Bronze.
Bronze. Fine. That's it. See, they have given the use of the solder alloy for welding electrical wires together. This could be asked in the objective form or 1 mark question. Okay, that's important. Fine. So now the last topic of the chapter is left. That is the chemical properties of the metals and non-metals. Huh? But before starting with that, I want to discuss this one thing here. Because I'm not able to recall it. If you can tell me, have I told you the exceptions here for all the metals and the properties of metals and non-metals? Have I told you the exceptions?
No, ma'am.
No,
No,
I've not told any exceptions.
no, I don't remember you told us anything.
Have you attended all the classes for this chapter, bache?
For this chapter, I'm attending
Huh?
no one class. Yes, all classes I attended in this.
Acha, fine. We'll give you the exceptions. Just 1 second. Fine. We can start with the exceptions then. So today we can quickly cover the exception part. Okay.
Okay,
In the next class, inshallah, we'll start with the chemical properties.
okay.
I would suggest you to write these exceptions where you have written the physical properties of metals and non-metals so that you do not miss this. Okay.
Okay.
Fine. Let's start to write it. The first exception. I think I have written it somewhere. I think we have discussed it, no? See, we have discussed these. Zeb,
I think I was not present.
you were not present. That's right. Anyhow, I'll repeat all the exceptions here again quickly. Acha, what are the properties of alloys? Can you tell me? Will their melting point be more or less than that of the pure metal?
Less.
Will their electrical conductivity be decreased or more?
Decreased.
Decreased. Now, exceptions first, very clear. Mercury. I'll write metal or non-metal. Metal, mercury, liquid at room temperature. Generally, the metals are solid at room temperature. Okay. Second one, sodium, potassium, lithium. They are very soft metals. Yes.
Ma'am, what did you write after potassium?
Lithium, Li. Poor conductors of heat, lead, mercury. Okay. Poor conductors of electricity, mercury, lead, titanium. Leave it. Okay. The next one. Uh, what else can we have here? Metals which are not malleable, that is zinc and all these. I don't think so that is needed. Should I scroll it down?
Ma'am, one second.
Which one?
Yes, sir.
Metals with low melting points. Metals generally have high melting point, right? These are the exceptions, bache. Mercury, potassium, gallium, very important. Okay. So these are some of the examples here. Is it clear? Any problem?
No.
Should I come to the non-metals?
Actually, 1 second.
Okay.
And
Gallium. It is gallium. Ga stands for gallium. Okay.
then what's
Now non-metals. Let's start with what? Iodine has luster, right? It is lustrous. Bromine is a non-metal. I mean, is liquid at room temperature. That is the only non-metal which is liquid at room temperature. Okay. Sulfur, carbon, phosphorus. These are mostly solid at room temperature. What is graphite made of?
sorry?
What is graphite made of?
Graphite,
Carbon, huh? Graphite is nothing but carbon.
carbon, and some other compound
No, no,
also.
no, 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 no,
Only
no.
carbon.
It's element, but it's pure carbon, huh?
Oh,
Diamond is also made of carbon only. Clear?
and can you scroll down?
Yep, yep. Fine.
Yes, ma'am.
Have you written this down?
1 second.
अच्छा, अच्छा.
Same done.
Last point quickly regarding this topic. Why is aluminium used to make utensils, huh? Cooking utensils. Why? Can you tell me?
Because it
Mm-hmm.
is
It has
not
good thermal conductivity. It has good thermal conductivity. Yes, it can actually conduct the heat very smoothly. Second, it's malleable. Yes or no? So it could be easily changed to this metal. I mean utensil from the metal form. And obviously high melting point. That's it. Clear, Zebunisa?
this one.
So that's it. Inshallah, in the next class, we'll. Oh, are you still writing? Just 1 second. Yes.